Oh,
Hello.
Hello.
how are you?
Good. And you?
Good, good. I'm Katerina. I'm the one that you exchanged emails with. Then the other three are outreach coordinators in the society, and Sophia will be co-hosting the session.
No.
Hi, Giovanni. Nice to meet you.
Nice to meet you.
Davide here is also Italian, but he's based in Switzerland.
Yeah.
Can you, Giovanni, can you just practice to share your screen just to see if everything is working?
Yes. Okay. One second.
Is it not working?
No, I cannot share my screen. Since let me just exit from the session and enter again.
Okay. Otherwise, we can try other things, but let's do that first.
Yeah. Thank you.
This is why we practice.
Can you guys share your screen?
Yes, I can. I think everyone should be able to upload.
Okay, that's fine.
Yeah, because we try to be able to like select the people that can actually share, but I don't think Google allows it. So we say either everyone or no one. So we just
Yeah, I think. Yeah.
No, I can share my screen, my pages on Google Chrome, but not my file presentation. I don't know why.
So it doesn't allow you to select the window, the proper
Yeah,
window?
it just allowed me to select pages of internet, Google Chrome. I don't know why.
That's
Strange.
weird. If you go, so like you have three things, you have the Google Chrome tabs, then you have like Windows and then full screen. I think if you click in the middle, which says Windows, I think is the English translation, and then there you can actually choose the PowerPoint.
Yeah, but it told me to activate the sharing, and I activated from my system, but I cannot share anything.
Okay, then I don't know.
Let me see.
Do we have people in the waiting room, Abel?
Yes, there's.
How many?
Almost 20.
Oh, very nice.
Slowly trickling in, but I think people just slowly coming in.
We were late last time, so I think people are starting to get used to it. It's fine.
Yeah. Oh yeah. Oh, he's back. Oh.
Let's try. Oh, okay. Oh, good.
Yeah.
There you
Okay.
go.
Oh, yes, you can see it.
Okay, perfect.
Okay. Right.
Very cool.
I'll share my screen and then I can let people in. Sorry. Where am I?
So now, Giovanni, we will let people in and we will present you and then the floor will be yours. Is that okay with you?
Thank you.
Yeah. You are in the wrong slice.
Oh. There we go.
There you go. Perfect.
Hello, everyone. Welcome to the first session of the Fashion Festival from the European Synthetic Biology Society. Today we have Giovanni Loprete to talk about the production of indigo blue to make more sustainable dyeing technologies a thing of the future.
Okay, so I think are we already ready to start? Or
Yeah.
Yeah. Okay. So without further ado, I will introduce our speaker today, and then we can give the floor to Giovanni. So Giovanni is a researcher at the University of Padua, where he works as a postdoctoral fellow in molecular science. He recently completed his PhD in chemical science, focusing on using biology and chemistry together to find more sustainable solutions for industry. His research explores how living systems like cyanobacteria, tiny organisms that can use sunlight as energy, can be engineered to produce useful compounds. One of his main interests is finding environmentally friendly ways to create indigo blue, the iconic dye used in denim, without relying on polluting chemical processes. Giovanni's scientific work has spanned topics ranging from harnessing photosynthetic energy to power whole cell catalysts to developing new strategies for plastic recycling, and even exploring advanced techniques to study protein interactions. And today, he will share how his team is re-imaging the production of indigo blue by combining sunlight, microorganisms, and innovative biocatalysts, offering us a glimpse of how science can shape a more sustainable future. And now Giovanni will tell us more about it. So the floor is yours, Giovanni. And you can try to share your screen.
Thank you, Sofia, for your introduction.
Yes.
So I will start sharing my screen, I think. Okay. I think now.
Perfect. Yeah, well, now we see the full screen. So perfect.
Okay, perfect. So today, thank you for your kind invitation and so also for your introduction. Today, I'm going to present to you one of the works that I carried out during my PhD program at the University of Padua in collaboration with several very bright scientists, such as Professor Bergantino, who is my supervisor, Marco Freie, Nicola Loncar from 𝗙𝗀𝘀𝗵𝗶cie, and my master student Francesco, and one of my colleagues, David. So today I'm going to present to you one example of how synthetic biology can help us and our society to move toward a green transition. So let me first introduce what is the green transition. With the 2030 Agenda of Sustainable Development, the industry must counteract with all the, and not only industry, but politics and all the nations as to counteract the effect of climate change. And with the 2030 Agenda, several agreements were made, such as the European Green Deal in December 2019, which goal is to achieve climate neutrality by 2050. And another important agreement is the Net Zero Industry Act. The goal is to decrease the amount of CO2 and try to trying to focus on sustainable production technologies and align the economic growth with environmental sustainability. So this is what the chemical industry is doing, trying to align economic growth with sustainability. And the European Union is pushing toward this transition. So in this context, we tried to do our best to produce the oldest dye, which is indigo. Indigo is the oldest and most consumed dye, which is produced and used for the dyeing of textile denim tissue, and is produced as 80,000 tons per year. It's the oldest since its history spans over 5,000 years, and it was originally extracted from Indigofera plants. But up to now, only the 1% of the total indigo produced represents the indigo naturally extracted from plants, just because the process is really complex and with very low yields. Nowadays, the indigo is produced mainly by the human Flagler synthesis, which is a very complex chemical process which uses toxic compounds and harsh conditions, but the main advantage is the very, very high yields of the reaction and of the process. However, several fermentative production systems were demonstrated and are present in literature. However, the yields are not sufficient to completely change and move from the chemical indigo to the fermentative and biotech indigo. Moreover, just to add another level of complexity, this molecule, the indigo, is really hydrophobic. It's soluble in few solvents and really unstable when solubilized in them. Moreover, its reduction, the dyeing cannot be directly done, but it's required a strong reduction to produce 𝗙𝘀𝗵𝗶𝗃, which is the soluble form and colorless, as if you can see on the left, which is a yellowish form, and then can be used for dyeing. Moreover, byproducts from the production are found in wastewater and in the final products. And the final product is the tissue, the denim jeans that we use. So, in this context and trying to produce this molecule, I'm going to show you now one of the incredible advantages of biocatalysis and synthetic biology. Since biocatalysis is a technology that consists in the employment of biological entities, such as entire organisms or their part, to catalyze a chemical reaction. Specifically, when we use an in vitro catalyst, we need to purify it, we need to immobilize or confine it for example, to immobilize it in a column. They are really good catalysts, since enzymes usually are characterized by quite good 𝗙𝗀𝘀𝗵𝗶 and radioselectivities. And moreover, enzyme engineering can allow us to produce enzymes that can react on non-natural substrates. And we can not only expand the panel of substrates, but we can also improve the kinetics of the enzymes. But today I'm going to show you and present you a whole cell process that consists in the production of an organism and in the utilization of the entire organism, of the cells of a consortium, to modify and perform a chemical reaction. In the whole cell format, the enzyme purification is not necessary, because the substrate is added in the medium and the product is secreted. However, these events are not sure to happen. However, another advantage is the less cost and a very high scalability, and this process maintains the advantages of enzymes, so 𝗙𝗀𝘀𝗵𝗶 and radioselectivity. However, these techniques present several disadvantages, such as the diffusion inside and the permeation of the product is not guaranteed. Moreover, the presence of a molecule inside the cell can lead to toxicity. Another disadvantage is that there are endogenous enzymes and endogenous molecules that can react exert their activity on the substrate or on the product, or our enzyme can react on a specific substrate, which is a cell's metabolite. What I'm going to present to you and show you today is the result of a quite interesting discovery, since it's the first time that in literature indigo is produced by a photosynthetic organism. We use Synechocystis, which is an eco-compatible organism, is a photoautotrophic gram-negative cyanobacteria that employs only CO2 and sunlight as its main source of carbon and energy. And as you can see, the CO2 is absorbed, and oxygen is produced by the cell for its growth. And moreover, its metabolism can be compared to a bacterial one. So it merges the worlds of plants and bacteria. Performing the photosynthesis, it's an ideal host for NADPH-dependent enzymes. NADPH is a substrate that is necessary for the reaction of several enzymes. And in this case, Synechocystis is well known from the literature to furnish and regenerate NADPH, which is a very expensive and unstable cofactor necessary for the reaction, directly from the photosynthesis. Moreover, its genome is completely sequenced. So it's a polyploid organism, and we have produced in our lab integrative vectors that can allow us to direct a transgene, an exogenous gene, in a neutral site of the cyanobacteria. So we merged all these advantages and tried to express the enzyme, an enzyme that is an indigo producing enzyme. Let me show what's present in literature. The highest yields reported are 18 grams per liter of indigo by fermentation of Escherichia coli, that was engineered to express naphthalene dioxygenase, an NDO. And this is the reaction, since in literature, indigo was shown to be produced in Escherichia coli many times, and researchers discovered the toxicity of indole and the opportunity to start the reaction from L-tryptophan, which is an endogenous molecule that can be converted to indigo by two enzymes, the tryptophanase A from Escherichia coli, and then the FMO, or indigo producing enzyme. What we cloned in Synechocystis was the FMO, the flavin-dependent monooxygenase, which is an NADPH-dependent enzyme that attracted particular interest due to the high reaction yields and purity of the formed indigo. It's well known from literature, and it's a study of our collaborator Marco Freie that produced up to 1.7 grams per liter of indigo, starting from 2 grams of tryptophan, when fusing the two enzymes, and the yields were different. So we tried to, as I mentioned, it was the first time for a photosynthetic organism to produce indigo. So we started from indole, and we tried to assess this second reaction, so the conversion of indole to indigo. The reaction is this one. So the indole is oxidated to indoxyl by the FMO, consuming NADPH, and in the presence of molecular oxygen, it's the dimerization from indoxyl to indigo appears, so producing the indigo dye molecule. So we engineered the strain, and we observed that when we put the indole inside the culture, inside the engineered Synechocystis, we observed dark blue clots attached to the flasks or to the tube. And so we tried to, it was a first indication that the molecule was secreted. And as you can see in a microscope magnification, in green, you can appreciate the Synechocystis cells, and in blue, you can see the crystals of the produced indigo. However, we tried also in the panel C, we tried to separate indigo from the cellular culture using a co-solvent, the DIMP, the diisononyl phthalate, but we successfully extracted it, but we observed, as known from literature, its degradation in the organic solvent. So we try to investigate the effects of the molecule indole in Synechocystis. And we observed that when we add indole to the cellular culture, we observe a phenotype that suggests that the cells are subjecting to cellular stress. We observed under the transmission electron microscope that the cells accumulates white spots which identity was compatible with PHB, polyhydroxybutyrate. So we tried to extract it and from a wild type and from a cellular an engineer's chain after the addition of indole, and we successfully extracted the PHB, since Synechocystis is a natural producer of PHB. And from the magnification in panel C, we can appreciate the indigo crystals in the PHB. So this was not our focus. We were assessing if the indigo production can be performed in a photosynthetic organism. But we had to struggle, and as I said you at the very beginning, when we want to use a whole cell, the whole cell format for the bioproduction of chemicals or molecules, we had to struggle with several disadvantages. And in this case, we observe a very high toxicity of indole, which was well known from literature in Escherichia coli too. So we had to struggle and to find the best conditions for the biotransformation and to allow cellular proliferation and to allow the conversion at the same time. Moreover, we had to struggle with the problem, since the extraction and quantification in organic solvents, directly in organic solvents from a cellular pellet is flawed, because the DMSO extracts pigments and extracts molecules, lipids from the cells. So basically, we had contamination. We couldn't quantify the produced indigo. So we struggled a lot, but we managed to produce a two-step protocol for indigo extraction and quantification that allow us to obtain an aliquot of pure indigo without contamination from the cellular debris. And this was a great result, because we could quantify our reaction and quantify produced indigo directly from the cells. So we had to optimize the reaction, and since we had to struggle with toxicity, and this was the first time that in literature was presented the production of indigo in a photosynthetic organism. So we tried to optimize several parameters, such as the highest substrate concentration in the biotransformation, and we select 1 millimolar indole. Then we try to assess the best time to stop the reaction, since we observed that we wanted to achieve very high yields and conversion, the maximum permitted from the cells, and we selected 72 hours. Then, since our promoter is well known to be in the middle from constitutive and light-induced. So we had to optimize also the best pre-cultivation optical density. So it is the optical density and when we grow the cell and then we stop them to concentrate and reach the final and working optical density. And we observed that the cells grown in the early exponential phase and optical density 1 gave us the best results. And this was in line also with the results presented in literature with other bioconversions. And then we assessed the best working optical density, and we selected the optical density 4, since we observed that if we double the number of cells inside the reaction, inside the flask for the reaction, we do not have very higher yields. And this is well known as self-shading. The problem with Synechocystis and with the photosynthetic organisms is that we cannot assume that increasing the optical density leads to higher yields, since a lot of photoprotective and self-shading effect happen. So we have a variability of the culture, and we have a variability of the yields too. So we merged these results, and we were able to obtain, we also optimized the light intensity for the reaction, and we selected the high light intensity as the best condition to obtain the best conversion, the highest conversion in our conditions, which was 87%, starting from 1 millimolar indole, producing 112 milligrams per liter of indigo. So in the context of green transition, we also wanted to assess if another method for the product extraction was possible. So we made a bioinformatics research in literature, and we observed that many works use materials, so solid state absorption, to extract and separate molecules from a culture. In this case, the molecule is indigo is, as I said, really hydrophobic, and is secreted from the cell. So we tested different materials, and we selected the polyamide netted fins directly inserted to the cell, to the cellular, to the reactor in the Corex tube, and we observed that when directly inserted in the culture, the indigo, the hydrophobic indigo, attached to it. So it was a great result, and we tested and we tried to use the net directly for reduction. And we observed that the net could be used for reduction, as you can see from yellow color to that is the leuco indigo, and we used the net for several extraction steps. So what we can conclude from this research? It's a very brief and interesting, and I mean quite beautiful example of how synthetic biology can be a tool to move toward this green transition, and how it's important not only to study but try to move to the production of molecules and chemicals that are used in the industry and nowadays. And this research represents the first time that photosynthetic organism is produced to express and convert indole to indigo. And but it is also an example of how an enzyme can affect, an heterologous enzyme can affect the cellular metabolism. And now what is ongoing in our laboratory is that we are moving to start the reaction from indole to tryptophan. So we are trying, even always in collaboration, to move and to engineer the strain, not only to start from tryptophan, but as a photosynthetic organism to convey and direct all the fluxes, the electron fluxes, toward the product. Since we cannot assume that 100% of light is converted into the product through the photosynthesis. But if we increase light, we can also start and increase, and a lot of photoprotective mechanism begins. So we now are also engineering the strain to ameliorate and stop all the alternative pathways for electron consumption and direct them all through the product and the photosynthesis. And this is the metabolic engineering that we are doing now. Moreover, that is not a few thing. We were able to isolate it in two protocols: optimize a protocol based on two-step organic solubilization, and a protocol without the employment of organic solvents, but only in the presence of polyamide netted film. With this, I thank you. I finished my presentation, and thank you for your attention. If you have questions, observation, I'm here. That would be glad to answer, to try to answer.
Great, thank you for your presentation. This is very cool science. I haven't worked directly into anything related to dyes, but I worked with Synechocystis for my master's dissertation about the electron flux aspect, actually, that you mentioned now towards the end. And my first question is related to that. Is there any modeling that has been done? Because you mentioned that you want to direct all the electrons towards this specific process. Do you know if anyone has ever done any modeling on how to start when it comes to this? What are the first steps? Have you guys already started that kind of work?
Yes, we are now collaborating with Professor 𝗙𝘀𝗵𝗶cie at the University of Padua. And what has been done now is that if we in kind of way, if we modulate the electron fluxes, the cyanobacteria reacts to reach the homeostasis.
Mm-hmm.
So it has been demonstrated that if we put an electron seek from NADPH, the photosystems increase their electron transport rate, but a lot of photoprotective mechanisms begins. So what we are doing now is to try to stop them, working on first in the geometry of the reaction of the reactor. We are now moving in two different ways: in the reactor and the geometry of the reactor and the engineering. We are interested in trying to do something with the flavin-containing proteins, but it's really hard. And Synechocystis cannot be managed as another organism. Few neutral sites are present in literature and known, so we had to do one single step and try to observe the effects. What we can do is that try to work with the flavin-containing proteins or other mechanisms.
Yeah. Okay. My second question is because you mentioned PHB.
Yes.
That's a bioplastic, right? My question is if you could use PHB as a sponge to help the purification of the dye in all downstream processes, or if you think it would be possible to improve the yield for two of these things, since the PHB was already increased when the compound was also increased. If you could express both of them, so you could, for example, use it as to sell a blue film, like a blue bioplastic. If you think that would be doable for your system or not.
Yeah, I showed here. I don't know if you can see this one on the right. Is a film of a bioplastic of PHB blue color, and the problem is that Synechocystis is a natural producer of PHB. The amount is really low, so if we want to do it, we had to move to parallel way, so increase PHB and then increase conversion. We never tested, but we can try.
Okay, that sounds nice. Thank you for your answers, Giovanni. I'm gonna now read the ones in the chat because we already have some. So the first one is asking, does increasing the high light intensity destabilize indigo within the 3 days of growth or production?
No, we did not observe this. We did not observe stabilization or degradation of the product. Okay. I think that the light inside the reactor is is used from the cells. So inside there is not too much light available to degrade the cell or to destabilize it. I see another question.
Okay. Yes, so another one is asking about the enzymes, if they are located in the plasmid or in the genome. So, and if you see some selection of cells that get rid of the genes since the product is toxic.
Okay, it's an interesting question. We used cloned and recombinate we use integrative vectors, homemade integrative vectors. So the genome is recombinated inside the genome of the cell. As a polyploid organism, we had to reach homoplasmy. This is an interesting question because the product is toxic. So basically, the substrate is toxic, not the product, but the substrate is toxic. So the cell can get rid of the gene. We did not observe it, but not in this case.
Yeah, it could happen. And I actually had a question, and then I can give the floor to Davide, but this is kind of a follow-up question from what we just been talking. Because if you lengthen the time that you want to culture them, you are increasing the chances that this negative selection would happen, in a sense, right? So I was wondering that you choose to culture it 3 days rather than 2, and the increase of the amount of indigo that you were harvesting was not that big, right? So was there any other reason why you chose to go for 62 hours instead of 48?
The reason that we chose we chose 72 hours is that simply we did not observe degradation, okay, and we had a slightly higher yield. But this was a decision taken together, and we did not.
Sometimes you just have to choose something, right?
Yeah, you have to choose something. Yeah.
Now I will give the floor to Davide.
Thank you, Giovanni, for the presentation. Super nice, very interesting. I was wondering about the possible applications to industry, like finishing the objective that you set for yourself. Did you do any consideration regarding potential costs and quantities that would be necessary for having a proper application into industry?
At this level, we made some considerations. At this level, we cannot, with these yields and this conversion, we cannot move from lab scale to industry scale because the yields are really low. If you see the yields of Escherichia coli, they are very, very high compared to Synechocystis, but it was the first approach. So the first results, the first indigo conversion and yields with Escherichia coli were low. So a lot of engineering research was performed to achieve these yields. So as a first pioneeristic work, we believe that some research and more engineering and optimization steps must be done prior the industrialization of the process.
Thank you.
I have more questions, which are more general. When you see applying this kind of research into the real world, do you see your cyanobacteria, for example, to grow in a water waste plant treatment facility or in something like that? How do you see that your research can fit in the circular economy model? Since you talked about the green economy at the start of your presentation.
Yeah. Synechocystis needs water, a few salts, and a buffer water to grow. That's a source of nitrogen, and that's all. So if we have them, I think that it's no problem of which source they come. If there is water, few salts, nitrogen source and the buffer, they grow. In the world, several approaches has been done to grow Synechocystis, not only in the reactors, but also in pools and in very big tanks. In the future, I see Synechocystis and I see photosynthetic organism to do something. We all, industries and the researcher, has to push toward that direction, because otherwise it could be difficult. And I appreciate these meetings, because people, industries, and researchers can see what's necessary to move toward this green transition.
What do you think is hindering cyanobacteria to be used more widely? Because I feel like a lot of policy people talk about bacteria, but very few talk about cyanobacteria and plants. I work with plants, so we're always talking with bacteria people, and we always say we just need sun, and they're like, yeah, that's great, but ours grows much quicker, is much more scalable, and things like that. What do you think it's hindering this progress for cyanobacteria to be part of the conversation as much as bacteria?
We have to improve the growth, cellular growth, and that's since many laboratories are switching from Synechocystis to other cyanobacteria that grow faster. We can do it if we work in the optimization of the photosynthesis, for example. And so with a better performing photosynthesis, we will have a better increase, a better growth, and a faster growth. But I would choose bacteria, cyanobacteria, but it's my passion. Just for the CO2 consumption and oxygen production, I love it. And they are green.
Let's keep it to this, and then we can pass into the chat questions.
I cannot understand.
Can you hear now?
Okay.
Just related to the sustainability and things. Did you guys look at all into the life cycle assessment of this kind of technology compared to the petrochemical alternatives that are now currently in the market?
No, we didn't perform a life cycle assessment, since the yields are very, very low. It's not enough. The yields is not enough to do it. But as I said, it represents a first step.
Mm-hmm. Davide, do you have any questions?
Yeah, I wanted to ask another question about the response to the indole, the cellular response. Is this kind of response observed for other toxic stresses for cells? Did you get any insight into how cells can defend themselves from this kind of stresses also?
In literature is known that indole is toxic not only for our Synechocystis but also for Escherichia coli at some concentrations. We did not further investigate in which sense it's toxic. It exerts its toxicity, but we, as I said, when you give a molecule, you alter the metabolism, you alter the fluxes, you alter whatever you have inside the cell. So we did not further investigate, but it's known. But there are several works in literature that prove them not only in our strain, in our organism.
Great. Since there are no more questions in the chat, we can end here. Thank you, Giovanni, for coming and for presenting your research. This kind of thing is great to hear about. We all already know some companies already working in this kind of technology, like 𝗙𝘀𝘀𝗵𝗶cie in the UK and some others like 𝗙𝘀𝘀𝗵𝗶cie and Denmark, which we'll hear about tomorrow. So you guys stay tuned. But yeah, thank you, Giovanni.
Thank you. Thank you for your time.
Sorry, what did you say, Giovanni?
Thank you for your kind invitation.
Okay.
That's fine. So next we're gonna have Ruth Lloyd, who is a PhD student in the University of Arts in London, who's working with calorifics in